Hello, everyone. Today we have Professor Barish here at the SAIR conference, and if you wouldn't mind just quickly introducing yourself to everyone.
Sure. I'm Barry Barish. I'm a physicist. I went to school in UC Berkeley, both undergraduate and graduate school, and then came as a postdoc to Caltech, and I've been at Caltech ever since. And in addition, I teach courses at UC Riverside and Stony Brook. My field of physics traditionally was particle physics, where I worked on large particle accelerators, have designed them and done a variety of experiments on them. And more recently, I was the leader of the development of the large gravitational wave detector called LIGO that discovered gravitational waves in 2015.
Mm-hmm. If you wouldn't mind, could you tell us why you decided to join SAIR as a founding advisory board member?
Yeah. Well, first, I'm a long-term friend of Chuck Ing's, and so I had some understanding of what he is interested in, what he does, and why he was creating this particular thing. I have my own views of the importance of using AI for science itself. We're using AI, large language tools, to hit society in general, but more traditionally, we've developed things in science and technology, and then they filtered out. What we need to do here is to concentrate on how best to use the development of AI tools and machine learning tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And for that goal, what do you think the purpose of SAIR is?
I think that SAIR has the feature that much of the work in this area is not being developed in universities, but being developed instead in companies and so forth, which is not the way much of computing has developed or other things have developed, where they've started first in a university and then developed outward. And the fact that it's then developed outwardly, it hasn't developed the same kind of, I would call it, thinking infrastructure around it of people who are maybe knowledgeable but not personally, don't have a personal investment in it, who help us guide where things should go, what happens. And that research in universities has always had the nice feature that it's a community that thinks about advances in understanding and in education and in science, and then has some both wisdom and knowledge of how and where it can be used, and then it helps influence where it goes. Here, it seems to me we're missing that somewhat. And so there's recently an effort that started inside the Department of Energy, and I don't know yet, it's just kicking off on AI and science, but otherwise they're pretty much absent. So I think this is the beginning of, let's say, an ambitious goal of somehow bridging this gap of somehow thinking and looking with a bigger view of how to use AI to advance science.
Mm-hmm. And your keynote reflects on 10 years of discovery since we have discovered gravitational waves. And what stands out most to you about how science has progressed, and what do you think is next?
I think that so the science has progressed in two ways, which I'll point out. One is we've just gotten better at it. Mm-hmm. In our case, that means making the instrument more and more sensitive. And so we have more examples of gravitational waves. That, to me, was kind of the traditional thing. It's what I would have expected to happen after we discovered gravitational waves. And I think we fulfilled those promises. Within 10 years, we've made an instrument that's 10 times more sensitive. We have hundreds of examples now of gravitational waves. What otherwise is interesting is how this has impacted other sciences and other ways of thinking. It's changed in some sense, it's changed what we know we can do in terms of precision as scientists. So precision isn't only important for gravitational waves, but in many, many things, we're limited by how precisely we can do things. And I would say that technically there's many innovations, but the underlying importance is the ability to kind of move technology forward in a way that gives you precision science, precision instruments. And to me, that's a long-term impact that we'll have, because precision of instruments is important everywhere, and how we approach making instruments precise requires some concentration on precision, not just improving instruments. So in a sense, the model for how we go about making a precision instrument, I think, is adaptable to many other problems.
Yeah, so it's the idea of focusing on precision rather than just generality.
Yeah, our size or ambition, those things. But really, I think the heart of what's, let's say, lasting and good in LIGO is the concentration on innovative technical and scientific advances that open up the ability to be more precise. In the present situation, we get a lot of publicity because we're starting to see on a big scale, it's only seen before on kind of atomic scales, quantum effects. And so quantum effects in a big scale are presently only seen in LIGO. But again, it's getting to the point where you're so precise that something like quantum effects come in. Here, where it comes in is the following. A quantum effect is always that you improve one thing and to make something else worse. You can't get beyond that. In our case, in a simple-minded way, you might picture that in order to make it a more precise instrument, we put in more and more light, which is more and more photons. And as we get more and more photons, then we get more measurements, and so it gets more accurate. But at the same time, each photon hits a mirror. And if I have more and more photons, many of them are hitting the mirrors, and it's actually putting some momentum on the mirrors and forcing them to move a little bit. And that's an imprecision. We on one hand, improve things by increasing the number of photons. On the other hand, we make it less precise by the fact that it pushes the mirrors. That's kind of a simple-minded view of the quantum effect. How do you get around that? You get around that by various techniques and dealing with quantum mechanics. So when we talk about very precision instruments, even on the scale that's not just elementary particles or something, but really a big instrument, we get around it by forcing the light to be configured such that it doesn't put as much momentum on the light. It's something, we have a name for it called squeeze light, but it basically doesn't put as much momentum on for the same number of photons. And so that improves things. So learning how to deal with precision at the level where precision's limited by some fundamental science or fundamental technology is, to me, other than the science we do, maybe the most important kind of technical advances.
Yeah, and as you have led a lot of discoveries with different disciplines, what do you think AI could do in terms of cross-disciplinary cooperations?
That's a really good question. I think the fact that we are able to do different things isn't because there's something unique in the human brain that does it, but everybody doesn't take the fact that they're able to do this and realize that the same technique maybe can help you do some other problem. So we tend to do that in the human mind. Somehow we figure out that we've learned something, but we can use it somewhere else. That gap, the fact is, if we can do it and use it somewhere else, AI can too. But the challenge is, how do we get the information of the creativity, if you want, of AI to realize that if it can solve this problem, it can also solve another problem. I don't have the answer to that, but it seems to me that's the challenge.
Yeah. There was actually a suggestion where we would have more disciplines apply their research to AI, and essentially the vision is that we want to really teach AI how to process the information and in such a way learn the process of reaching that point. So it's essentially learning the processes with which we reach our solutions, and then with how that works, we can then apply it to different fields, and you have basically a connect between fields that would maybe otherwise not be so connected.
Yeah, I think that's very important to develop, actually, because it's one of the few ways which we're able to kind of qualitatively do better than something like AI, which it concentrates on one area and does very well. But we're very good at, as humans in the human brain, at learning how to solve problems because we know how to solve another problem. That's a different thing than using all the information to solve this problem. But the fact that we can solve different problems is something we're very good at. And it seems to me should be one of the main challenges to advance AI. If you develop AI so it's really good at something, why can't we, just like we do, apply it quickly to something else, what you've learned through AI to something else?
And another thing is that, do you think AI will greatly affect what scientists ask rather than how they ask it? For example, with a lot of algorithms, we are now able to simplify a lot of processes that we would otherwise not be able to. I think that this influences fundamentally what people can aim for in terms of scientific discovery, aiming for some things that we otherwise would have not been willing to spend the time on.
Yeah. I think the answer is clearly yes, and we're just in the infancy of doing this. We've always tried to do that, but we haven't had as good a tool as AI. So we do, as a physicist who does fundamental physics, we do a lot in order to study what we're able to do or have some idea what we're able to do. We do a lot of simulations, modeling, and so forth, but not use knowledge very well. So just knowledge that we may have. So somehow integrating AI into the concept of thinking about what to do, I think, is a really open and fruitful direction for AI to develop. Because we do it, we don't have anything unique about us to do it, that AI should be able to use what it's learned here to do somewhere else.
As of current, what do you think is missing for that breakthrough to happen?
Maybe experience. I mean, AI is, I don't think it's fundamental. I don't think there's some fundamental barrier. I think the problem is that mostly AI is so new that people are kind of at their limit to use it for whatever they're using it for. So we're not yet able to do what we do with regular instruments, which is we have an instrument and then we immediately think it could be used for something else. With AI tools, we're probably not there yet because it's so much in its infancy. I don't think there's anything fundamental that holds it back. It's as long as you're able to solve the problem, starting to solve really hard problems with AI itself, it seems presumptuous to look at using it somewhere else. But I don't think it's premature. I think it's the way technology and science have advanced otherwise. And there's nothing unique about the way we do it otherwise that AI couldn't do.
And in general, what do you think is something people mistake about using AI in science?
Say it again.
In general, what do you think is something people typically mistake about using AI in science?
It depends who we mean by people. If we talk about people who do science, I think that there's still a fair amount of ignorance among the scientists of what the capabilities are of using AI. If we talk about the fact that our main tools to do science, other than technical things, are mathematics, and AI is more language at this point, based around language. And so it doesn't automatically appear how it can directly play the right kind of role in science. So we need some, among scientists, a better understanding of what AI means, and not just that it's a big compilation of language.
Right. Yeah, and I think it's very important to understand this because AI is not a completely new thing because while we have the rapid expansion of LLMs now, AI has been a thing in algorithms and such since
Right.
long ago, and it's been widely used, at least from what I've seen. It's not exactly a niche thing, but it's just I think that there is some mistaking for what is specialized AI for science and what is generally used, and there's a very big difference between the two.
Yeah, I agree with you.
I think that's about it.